At 8:15 p.m. Pacific Time, SpaceX's Crew 1 Dragon capsule docked with the International Space Station, where it will stay for the next 6 months. And not long after, the Stage 1 Falcon 9 booster rocket touched down on the Just Read Instructions drone ship somewhere in the Atlantic. This marks the first time since the Space Shuttle was retired that astronauts were delivered to the ISS from American soil. It effectively ushers in a new era of spaceflight for the US. The crew will be conducting a variety of experiments aboard the ISS, and in December, they're going to be receiving a supply cache carrying some more experimental materials, including rock-eating microbes that will test the viability of converting lunar regolith into useful materials for future missions. We're taking a look at the viability of breaking down regolith, the risks and advantages, and looking forward to the future of spaceflight. I'm Eric Malachite, author of Echoes of Olympus Mons, and this is Science Get. In December, astronauts aboard the ISS will be monitoring microbes that can interact with rocks. NASA hopes that the experiment could lead to the development of more advanced life support systems that will break down regolith on the Moon and Mars and convert rocks to soil for plants. The aim is to allow astronauts to build bases with fewer supply drops from Earth. But what exactly is Experiment Bioasteroid? This isn't the first time we've talked about lunar regolith, and it probably won't be the last. We've mentioned how the stuff was a nuisance to the Apollo astronauts, getting inside the lander and all over the astronauts' suits and how it wore them down over time, some to the point where a breach was possible. We also talked about some inventive technologies that might be able to use moon dust to create roads, satellite dishes, and ways to filter the stuff out of mission-critical landers, vehicles, and habitats. But what if you could use it for life support systems? Well, the bioasteroid experiment will test how microbes form layers on the surface of rock material inside a liquid medium, and how they might alter the release of elements like iron 2, magnesium 2, calcium 2, and a variety of other elements. The goal here is to develop biological mining processes, or biomining for short, that will help produce soils and economically interesting elements. The experiment will also test how those microbes function in microgravity and how it might affect their interactions with rocks. It will also inform us on how mixing regimes, as well as how convection currents and sedimentation behave under these conditions. So what else could biomining help produce on the Moon? Well, to figure this out, we're going to have to look at what lunar and Martian regolith is composed of. That's right, we're getting into some speculation. Lunar regolith isn't like Earth's soil. It's extremely dry, and it's composed of metallic iron and various types of glass. Iron is useful enough on its own, but what about other applications? Well, we do know that there is water on the Moon, and while hydrogen is not common in lunar regolith, the solar wind continually bombards the surface of the Moon with hydrogen atoms before quickly stripping it away. Guess what else is present on the Moon? Oxygen. Lots and lots of it. In the samples brought back by the Apollo astronauts, it was found that regolith contains at least 40% oxygen. Are you thinking what I'm thinking? Because I'm thinking that it may be possible to use biomining, possibly with these microbes or others used in subsequent experiments, to produce air for moon habitats continually. The hydrogen part might be a bit more difficult, and it may not be possible through biomining. But hey, that's why this is speculation, right? But speculating further, could we set up collector arrays across the Moon's surface designed to collect hydrogen coming in from the solar wind? If it is rare, we might need multiple sources of hydrogen to ensure there's enough to go around to produce air continually. The production of air on the Moon would go a long way to establishing a base for our astronauts and reducing the burden that Earth would have to bear in resupplying them. But there are a few other things about the Moon that may make it a fantastic spot to set up shop, especially if we're hoping to explore the rest of the solar system and someday interstellar space. One of those is helium-3, which may be useful as fuel for fusion-powered spacecraft in the future if we can ever get fusion technology right, a topic worthy of its own video. But also rare earth metals, which are extremely difficult to mine on Earth, like yttrium, lanthanum, neodymium, and gadolinium. These rare earths are useful for creating lasers, powerful magnets used in our cell phones and electric cars. We see what you're doing, Elon. and tough metal alloys. Effectively, biomining could allow us to produce a lot of materials on the moon that would be needed to construct our bases, further reducing the burden of NASA and private space companies to resupply building materials. What's more is that many of these rare earths and oxides are present in Martian regolith as well. And since there is water on Mars, we could probably use a combination of biomining and electrolysis to produce all the hydrogen we need. Curiosity also detected unusually high levels of hydrogen in Mars's North Pole. But if our Mars and Moon colonies are to survive, they're going to have to be able to produce their own food. And luckily, that seems to be the primary goal of BioAsteroid. The microbes chosen for BioAsteroid are Penicillium simplicimum and Sphingomonas desicabilis. Penicillium simplicimum is an anamorphic species of the household family of molds that typically grow on food products and can be made into various medicines, including penicillin, which, as a side note, I'm deathly allergic to. But since Penicillium simplicimum can help promote plant growth, the thinking here may be that this could aid in establishing lunar or Martian greenhouses. It's not currently known how volatile Martian or lunar regolith will be to plant life, but it's possible that they're simply not suitable for growing. Mars also has harmful perchlorates like chlorinated hydrocarbons. These are really poisonous to human beings. In The Martian, by Andy Weir, marooned astronaut Mark Watney is forced to use his crew's poop to farm potatoes on Mars. Could it be that simple? Well, yes and no. While Weir did do copious amounts of research to ensure his novel and its excellent film adaptation, which I desperately need to give another watch, was as scientifically accurate as possible, Weir didn't know about the harmful perchlorates present in Martian regolith. So does the presence of them hurt our chances of growing plants on Mars? Fortunately, all we need to do to fix this problem is rinse the regolith in water, and that should get rid of the harmful chemicals. It could be that BioAsteroid is the first step toward engineering a mix of microbes that are guaranteed to convert regolith into soil that plants will grow in. And botany is no joke though, and there are plenty of places on Earth where the soil has degraded to the point where crops won't grow. If NASA is successful, could we see the development of technologies that could effectively help restore soils on Earth too? Okay, well that's great for soil, but what about Sphingomonas desicabilis, the other microbe they're working with? Well, the bacteria are found in the soil crust of the Colorado Plateau. Sphingomonas have a variety of different species, but their primary characteristic is that they're capable of surviving in environments with low concentrations of nutrients. They're also responsible for a bunch of infections in humans that are typically easy to resolve with antibiotics. Sounds ideal for space, doesn't it? If you enjoyed this video, drop me a like and let me know what kinds of things you think we could make from regolith through biomining. And be sure to smash that subscribe button and ring that bell to never miss an episode of ScienceGet. I'm Eric Malachite, and I'll see you next time.